Alright, good day everybody. I hope you've had a great day, a great 24 hours. Before we begin taking notes, I want you to make sure that you've got your highlighters out, because you'll need probably about at minimum of 4 different colors of highlighters. Okay, so take about a minute to get those highlighters, or you could use different colored markers, different color crayons, just something that has 4 different colors. So today we're going to continue working with our polynomials, and we're actually going to be looking at analyzing the graph of our polynomials. Okay, so sometimes we call it key features of polynomial graphs. Sometimes it's referred to as critical points, but basically we're going to be analyzing the graphs. So before we get into analyzing, let's look at a couple of our vocabulary words. Alright, our first one is a critical point. What exactly is a critical point? Okay, well, a critical point is simply a point, or it could be points, where something on the graph changes. Now, obviously, there is a more formal definition, but I just like using this very general definition right here. So again, a critical point is something, it's a point on the graph where something changes. Instead of going left, it makes it go right. Instead of going up, it might make it go down, etc., etc. Alright, so relative maximum. Alright, now we all know what a maximum is. A maximum is the highest value. So if we're talking about a graph, a maximum would be the highest point. But look at this graph right here. We can see that this is the squiggly line, so this is a cubic function. And we know that a cubic function goes up forever. So if it's going up forever, do we actually have a maximum? No, because it keeps going up forever. It's going to infinity, so it doesn't stop. It doesn't have a maximum. So what we do in order to look at maximums, we look at what is called a relative maximum. Okay, a relative maximum is simply the highest point, or it could be points, so you could have more than one relative maximum. The highest point on an interval, and we can also call interval a section of the graph. Alright, so looking right here, now usually, excuse me, a relative maximum is going to occur at a vertex. So looking right here, in this section of the graph right here, this is the highest point of that section. So this section right here is known as your relative maximum. So basically it's the highest point. And you might have more than one point. That's a relative maximum. Alright, speaking of more than one point, what is an absolute maximum? Okay, an absolute maximum is simply the highest of all relative maximums. Alright, so in looking at our diagram right here, I see that B is a relative maximum, D is a relative maximum, and F is a relative maximum, because they are the highest point in each little section right here. But of these three relative maximums, f happens to be the highest, so it is called not only a relative maximum, but it is the absolute maximum of this graph here. Now, obviously, if we have relative maximums, we're also going to have relative minimums. Okay, so a relative minimum is almost the same wording, but instead of saying the highest point, it is going to be the lowest point. Because again, this is a cubic function right here, because we can see by the squiggly. It's going down forever, so it's going to a negative infinity. So if it's going down forever, we don't have a true minimum, because it never stops. So we have that relative minimum. And a relative minimum is simply going to be the lowest point, or points, because you can have more than one, on an interval of a graph. And most of the time these do occur at a vertex. So right here, this is the lowest section. That is the lowest point. So this right here is our relative minimum. And just like with the absolute maximum, we're also going to have an absolute minimum. So the absolute minimum is the lowest value or point of all the relative minimums. Okay, so going back to this same diagram, we can see that A is a relative minimum, C is a relative minimum. Now it printed a little weird, but F is a relative minimum, and it's actually supposed to be, excuse me, not F, but E. E is supposed to be a little higher than C. So out of A, C, and E, we can see that C is the lowest, so that would be the absolute minimum. All right, and then our last vocabulary word, point of inflection. All right, we know that when we had absolute value graph, we had a vertex. When we had a quadratic graph, which is a parabola, we also had a vertex. For our square root, we had a beginning point but no end point. That beginning point was called the initial point. Well, a point of inflection, we are going to use that for our cubic functions. Okay, the point of inflection is this point right here in the middle. It's your inflection point. What a point of inflection is, it's the point on a cubic function where the graph reflects, or as y'all like to say, it flips. If you notice right here, this graph is opening up, but then it hits the point of inflection and it opens down. Okay, give you a few more seconds to finish copying that down. All right. So there are 9 things of interest for critical points. Okay. All right. The first one is our domain and range. Now, we've already worked with domain and range. All right. We know that domain on a graph always reads the graph from the left side of the graph to the right side, and the range reads the graph from the bottom of it to the top of it. Your domain and range is going to be the only one that either uses a set of parentheses or a paren, or a set of brackets, or just a single bracket. All right, in behavior. Okay, think about what the word in behavior had. The words that in behavior have in it. It has the word end, so we're talking about something at the very end, and behavior. How does the graph behave at the end? Okay. All right, so if you notice right here, we got these weird looking statements. These are the 2 statements you're always going to have to write down when you're talking about in behavior. At least in Math 3. When you go to upper level math, it's going to change a little bit. You're going to have some limits in there, but for right now, these are the 2 statements that we're going to use. Okay. So let's talk about what this is. As x approaches positive infinity, what side of the graph is x going to be going to positive infinity? Well, that's going to be the right side of the graph. So this right here is just saying, hey, on the right side of the graph, because we're talking about the right side where x is going to positive infinity. So this is simply a fancy way of saying, hey, on the right side, what is f of x approaching? Well, we know f of x is just a fancy way of saying y. So it's asking, where's the graph going on the right side? Is it going up or is it going down? So most of the time, this is either going to be a positive infinity or a negative infinity. Okay, so if the graph is going up forever, it's positive infinity. If the graph is going down forever, it's negative infinity. All right, as x approaches negative infinity, which side of the x-axis do you have the negative values? Well, that's on the left side. So the left side is where your negative infinity is going to be. So this part of the statement right here is just a fancy way of saying, hey, on the left side of your graph, what are the y values doing? So on the left side, if it's going up forever, it's going to positive infinity. On the left side of the graph, if it's going down forever, it's going to negative infinity. All right, your relative max and relative min. All right, we're not going to write these as ordered pairs. We're either going to write it as a fancy way, we're going to say the y value at the x, or we might just say the y value. Because if you're talking about a relative max and a relative min, max and min, that's a vertical. So since we're talking about a vertical, we're talking about the vertical axis, which is the y. So it really wants to emphasize the y value. So like, for example, if this point right here was 9, 2, we would actually write that the relative max, because that's the highest point, we would say 2 at the x value of 9. You want to emphasize the vertical or the maximum or the minimum, which is the vertical value, which is your y. So it's always the vertical value first, and then your x value. All right, intervals of increase. Okay, you're only going to use the x values, and you're always going to do a parentheses. So a good way of thinking about intervals of increase, you look at your graph and you ask yourself, where on the graph are you walking uphill? Intervals of decrease, again, you're only going to list the x values, and you're always going to use the parentheses. So decrease, you want to ask yourself, where are you walking downhill? Okay, intervals where f of x is greater than 0. Alright, so remember f of x means y. Greater than 0. What kind of numbers are greater than 0? Well, that's positive. So this is just a fancy way of saying, hey, where are your y values positive? Well, we know that the y value is positive above the horizontal axis. So it's above the x-axis. So you're going to look for any pieces of the graph above the x-axis. Intervals where f of x is less than 0. So what kind of numbers are less than 0? Well, negative numbers are less than 0. So it's asking, on what part of the graph do you have y values that are negative? And we know those y values are negative when it's below the x-axis. And then the final thing that we're going to look at are your zeros. All right, zeros are also known as your x values or the x-intercepts. So there are 3 other words that mean zeros. X-intercepts, solutions, or roots. They all mean the exact same thing. And what the EOC likes to do, from the release versions I've seen, they like to interchange these words. So sometimes they might say, given the following zeros, find the remaining roots. Or 15 is an x-intercept, what are the other zeros? So they like to interchange the words within the same set of directions. Okay, so this is a little bit of an explanation of what we'll be doing, but sometimes just reading it doesn't really, fly. So let's actually look at the examples. Alright, so what I want you to do right here is I want you to connect all these right here. So let's connect these. Alright, so the first thing we're going to look at is what type of function is this? Alright, so it's not my squiggly line, it's not a parabola, it's not a straight line. So I know it's not linear, it's not quadratic, and it's not cubic. What it is this W shape. Alright, when you have that W shape, it is going to be a quartic. Okay, so that W shape, whether it's opening up, that W is opening up, or the W is opening down, it's going to be a quartic. Okay, and that means that your highest exponent, if you have the equation, would be an x to the 4th. Alright, so we want to start off by determining whether this is an even or an odd degreed function. Okay, and notice I said even or odd degreed. So we want to know what kind of exponent is this. Now, well, I kind of already know since I recognize the shape. The biggest exponent is a 4, so that would be even. But we can also recognize this as an even degreed function for one simple thing. When both ends open the same direction, it's going to be even. So notice the end piece over here is going down, the end piece on the right side is going down. That both end pieces are going the same direction, so it's an even degreed function. If it was an odd function, the ends would go opposite directions. Okay, so if you think about it, opposite starts with O, odd starts with O. That would be something like a cubic function. So see how one piece of the cubic is going up and the other piece is going down. They're going opposite directions. So cubic function is an odd degree function. Something else that you might be asked is, what is the sign of the LC? The LC stands for leading coefficient. What is the sign of the leading coefficient? Okay. All right. So if it's an even degree function and both pieces open up, the leading coefficient is positive. If it's an even degree function, both ends open down. Since it's opening down, it means it's been reflected over the x-axis, so that would be a negative leading coefficient. If it's an odd function, and it starts low and works its way up, so you're rising from the left to the right, like a slope, rising left to right, we know it's a positive slope, so it would be a positive leading coefficient. And if it's odd and it falls from left to right, so think about it. If that was a slope right here, that would be a negative slope, wouldn't it? It's falling. It's going from a higher y value and ending up at a smaller y value, so that is negative. Now, one of the ways I always tell students to think about the odd functions, if you put your pencil on the end pieces, connecting them with that pencil, what kind of slope would that be? That would be a positive slope. On the other hand, look at this one right here. If you connected those two end pieces, what kind of slope would that line be? That would be a negative slope. Alright, so let's get into our key features of this function here, this quartic function. Alright, so we're starting off being asked, what is the domain? Remember, domain is always from left to right. Okay, well, I can see that it's going to the left forever, and I can see it's going to the right forever. So when it goes left and right forever, but it's going to the left, it's going to negative infinity on the x-axis. And remember, domain always deals with the x values. And if it's going to the right on the x-axis, it's going to positive infinity. So we're going from negative infinity to positive infinity. Your negative infinity will always be on the left side of your interval, and a positive infinity will always be on the right side of your interval. The range deals with the y values, and it always goes from bottom to top. So look at this one. This one is going down forever. So if it's going down forever, what is forever in math? It's infinity, right? And down is negative, so this one is going to negative infinity. And infinity is always going to have a parent, so this would be negative infinity. But notice, from the bottom to the top, what is the highest y value that we use? Well, the highest y value that we use is a 5. This has a closed circle, so it's going to be a bracket. That means it's inclusive. It includes that value. Alright, in behavior, as x approaches negative infinity. Alright, where's x negative? X is negative on the left side. So it's saying, hey, on the left side of the graph, what's the y doing? Well, the y is going down. It's going down forever. So what is it approaching? It's approaching negative infinity. As x approaches positive infinity, where is x positive? What's on the right side? So this is saying, hey, on the right side of the graph, where's your y value going? Well, it's going down forever, so it's also going to negative infinity. If it's an even function, these statements should always be the same. If it's an odd function, these statements are going to be opposite. One's going to be positive and one's going to be a negative, depending on what kind of function it is. Alright, relative max. Alright, so let's find our relative maxes. Okay, alright, this is a highest point, so this is a relative max. And here's another highest point, so this is a relative max. So we have two relative maxes. So we're going to say 5 at negative 4, 5 at negative 4, semicolon, and then 3 at 2. Now sometimes they might just have a 5 and just have a 3. Sometimes they only do just the y value. Alright, the relative means. Alright, so look for your lower vertices. Well, we only have one vertex that's low, so that's going to be negative 3 at negative 2. The y value at your x value. Alright, so coming right here, intervals of increase. Alright, so this is where your 4 different colors will come into play. Alright, so remember, intervals of increase are where we are walking uphill on the graph. So let's start from left to right. So right here, are we walking uphill or are we walking downhill? Well, we're walking uphill. So this is an interval of increase. So we're going up, walking up, walking up, walking up. We hit that vertex and we start walking down. So this piece is not an interval of increase. But we hit this vertex and we start walking up. So we got another interval of increase. We hit that vertex and we start walking down. So that's not an interval of increase. So we have 2 intervals of increase. What we're going to do is we're going to look at these and we're going to see where do they begin and where do they end. If you have an arrow, it's always going to be some kind of infinity. And remember, we're only dealing with the x's. Okay, so where does this interval start? It starts at an infinity, but on the x-axis it would be negative. So it's starting at negative infinity. And what x value is this one stopping at? It is stopping at an x value of negative 4. Now, all of these right here are always going to be a pairing. They're never going to be a bracket. All your intervals are always a pairing. Since we have more than one interval of increase, we're going to union that with the second one. So this one is bounded. It has a beginning and an end, so that makes it really nice. Where does this one begin? It begins at negative 2. Where does this interval of increase stop? It stops at a positive 2. And there, folks, are your 2 intervals of increase. All right. Let's look at our intervals of decrease. Well, if we're not walking uphill, then we're walking downhill. So here's an interval of decrease because we're walking downhill. And what is actually happening here is that your y values are getting smaller. So your y values are decreasing. All right, and then right here at this vertex we start walking downhill. So we just so happen to have 2 intervals of decrease. All right, this one is bounded, so that one's pretty easy. We know where it's beginning and we know where it's going to end. Okay, so this interval begins at negative 4. So we've got negative 4. Walking downhill, walking downhill, walking downhill. And it stops walking downhill at negative 2. So that's your first interval, and then we're going to union it with the second one. Our second one starts at an x value of 2. And remember, all the intervals are always going to have parents. So it's going to be inside parentheses, no brackets. All right, so we're walking downhill, downhill, downhill. Well, it's downhill forever, isn't it? Now, this is where students get a little confused, because I see a lot of people come out here and say, well, I know it's infinity because it's got an arrow. And they'll come in here and put a negative infinity. But the x's are not negative on the right side. That's actually a positive infinity. So it's really easy to say, oh, it's pointing down, it's negative. But remember, these only deal with the x values. We're never going to look at the y for your intervals. Okay, we're always going to write down the x's. All right. Then we have intervals where f of x is greater than 0. So we're looking for y to be positive. Where is y positive? All right. So if I come right here and I choose this point, do I have a positive y value? Yes. If I choose this point right here, do I have a positive y value? Yes. If I choose this point right here, do I have a positive y value? Yes. So all my values above the x-axis are positive. So here, f of x is greater than 0. And then also right here, any point I choose would have a positive y value. So this interval right here is also an interval where f of x is greater than 0. Now these are bounded, so that makes it pretty easy. So let's see, let me come right here. All right, from what x value to what x value? Well, from -5 to -3, that part is above the x-axis. So -5 to -3. Because any y value, any output, is a positive y. All right, for this one right here, this is bounded. It has a beginning and it has an end. So it goes from a 0 to a 3. So we're going to union that with 0 to 3. All right, and then our last interval to look at is where f of x is less than 0. So we're looking for the y values to be negative. Okay, so that's any piece of the graph that's below your x-axis. So it would be this piece right here, this piece right here, and this piece right here. All right, so let's write this out. All right, remember we're only dealing with the x's. All right, so this has an arrow on it, so I know it's going to be infinity. So what type of x is on the left side? Well, that's negative. So this goes from negative infinity, and then right here it stops. So it stops at -5. And the reason why it stops at -5 because at the x-axis, y is neutral, it's a 0. And then beyond the x-axis, it becomes a positive y. Okay. Our second piece is bounded. It has a beginning and an end. So we go from -3 to 0. So when you union that with -3 to 0. And then finally we got one more piece. All right, this piece right here starts at 3, and it's going to the right forever. So we got 3. Now remember, we're only dealing with the x's, so it's got an arrow, so I know it's going to be an infinity. What kind of x is on the right side? Well, it is positive. Be helpful if you could see it, wouldn't it? And then finally, our last thing that we're going to write down are our x-intercepts. So where are our x-intercepts? Okay. All right, so left to right, our first x-intercept is a -5. Then we've got a -3. Then we've got a 0. Then we've got a 3. And remember, zeros are known as x-intercepts, solutions, or roots. I know that's a lot to take in at once. All right. Now, these are a little hard to see, but this is a U-try problem. I'm going to come in here and write these a little better. All right, that point right there is 2 and 56. This point right here is -1, -25. This point right here is 5, -25. This point right here is 4, 0. This point right here is 5.74 and 0. This one obviously is 0, 0. This one right here is -1.74 and 0. Alright, so if you'll pause the video for about 8 minutes, and I want everybody to give this a try. Okay, so let's see how you did. Alright, here's that W shape again, so I know this is a quartic. Alright, is this even or odd? Well, both end pieces are going the same direction, so it is even. What is the sign of the leading coefficient? Well, both end pieces are opening up, so that is positive. Alright, for the domain, well, it's going left forever, and it's going right forever, so it's all real numbers, so negative infinity to positive infinity. Alright, for the range, that goes from bottom to top. So coming from the bottom, the first y value that we use is a -25, and they have closed circles there, so it's a bracket, -25, and it's going up forever. So it's approaching a positive infinity. Alright, for our end behavior, as x approaches negative infinity, which side of the x-axis is x negative? That would be the left side. So on the left side, what are your y values doing? They are going up forever, so they are approaching positive infinity. As x approaches positive infinity, where is your x positive? Well, it's on the right side, so this is saying, hey, on the right side of your graph, what are the y values doing? So the y values are also going up forever, so they're going to positive infinity. Alright, the relative max. Alright, so for your relative max, this time we only have one highest point, so that's going to be 56 at 2. So 56 at 2. Now again, sometimes remember they might just come in here and just put a 56. Sometimes they just put the y value. The relative minimums. Alright, well, we got two relative minimums. Okay, we got -25 at -1 and -25 at 5. Alright, intervals of increase. Alright, so left to right. Folks, are we walking uphill or downhill? Right, we're walking downhill. But we hit this vertex right here and we start walking uphill. So this is an interval of increase. Hit that vertex, start walking downhill. Hit this vertex and start walking uphill. So we have two intervals of increase. So from what x value to what x value? Alright, so from a -1 to a 2. So here, -1 to a +2. Then we're going to union that with the second piece. Alright, this piece starts at an x value of 5, and it's going to the right forever. So forever in math, it's infinity, and since it's on the right side, it's going to be positive. So this is positive infinity. Well, if it's not increasing, then it is decreasing. So here, notice from left to right, we'll be walking downhill. uphill, then this one is going to be downhill. So this first one has an arrow. Alright, so it's going to start off with an arrow, and since it's on the left side, what kind of x's are on the left side? That would be negative, so we're talking about a negative infinity, and it stops at a x value of -1. Alright, we're going to use that. Alright, this one is bounded. It has a beginning and it has an end. So again, a little person is walking downhill. So this is an interval of decrease. So it begins at 2 and it stops decreasing at 5. So from 2 to 5. Alright, so where is f of x positive? Okay, where is f of x positive? Well, the positive y values are above the x-axis. So it would be this piece right here, because that piece is above the x-axis. It would be this piece right here, because that's above the x-axis. And it would be this piece right here, because that is above the x-axis. Alright, so let's write this down. Alright, this has an arrow. So I'm going to put my infinity. Since it's on the left side, what kind of x is on the left side? All the x's on the left side are negative, so that would be a negative infinity. And it's stopping at an x value of -1.74. This one is bounded. It begins at 0 and it stops at 4. So 0 to 4. So again, what does this mean? That means that any value we choose off our graph, no matter where it is, it would always have a positive y value. Okay, so any piece, any point off any of those green pieces would always have a positive y value. So we got this piece and that piece, and let's get this last piece. This last piece starts at 5.74, so union that with 5.74, and it's going to the right forever, so that is positive infinity. So that's 5.74 to positive infinity. I know I got some stuff written right there. And then finally, for our intervals, where is f of x less than 0? That means where is y negative? Well, y is negative below your x-axis, so it's this piece right here and this piece right here. Now, fortunately for us, these are bounded, so we have a beginning and an end. Alright, so this one begins at -1.74 and it ends at 0. Since it has a second piece, we're going to union that. The second piece begins at 4 and it stops at 5.74. And then finally, our x-intercepts. Alright, so we got a -1.74. We've got a 0. We've got a 4. And we've got a 5.74. So hopefully you did okay. And if you got stuck at something, hopefully you saw what we had to do here. Alright, so you got 4 homework problems. I think I'm telling you to only do 2 of them. I can't remember. You need to look. You need to open up the homework link and see which problems I want you to do. I can't remember if I am asking you to do 2, 3, or all of them. But if I ask you to do that last one, I want to show you how to get that last one. Okay, so this is not the same problem, but it's going to be one similar to it. And that last one, they give you the equation. They don't give you the graph. So you're going to have to find your critical points. So you can go to Desmos. Alright, and you're going to type in the equation they give you. So like if I gave you this right here, we would type in x minus 3 times x plus 3 squared, and then we got plus 5. All right. So to get my critical points, I know I need a vertices. So if you just tap your graph, you'll see some points pop up. So here's my vertex. Here's my vertex. X-intercept, x-intercept, x-intercept. And there are your critical points. Desmos makes everything really nice. We used to have to figure this out by hand in the old days. That took forever. But again, all you do is graph it. So you would come right here, you do a quick sketch. It does not have to be a perfect sketch by any means. And like right here, I put a -3, 5. Right here, this is, -3.85. This point right here is -2. This point right here would be 1, -27. And this point right here would be 2.85 and 0. And that's all you would do. All right. Make sure you put your name and date on the notes and submit those, please.